Hello, welcome back to the stream. Looks like we're live on YouTube. Are we live on Twitch? Yeah, we're live on Twitch also. Well, welcome back everyone. Back to our usual work in progress, electronics, engineering, reverse engineering, CAT, all of the above. And yeah, here I am, and here's the work in progress. So this is our work in progress robot for, oh geez, I've said work in progress so much. Let's just say it a few more times. Anyway, this is the thing we're working on, and now it's in progress, as it has been for a while. So this is a kind of flying camera that's designed to be, you know, a decent way of interacting with my weird cat on the internet. It's got a long list of bugs at the moment, but it's mostly built. So it's really at that point in development where we've kind of iterated on the design enough to get something that seems to mostly work, but there's some polishing needed, which is a pretty good place to be at. So I started a GitHub issue tracker. There were several repos for this project. So everything, sorry, I'm trying to switch my keyboard and mouse over there and using completely the wrong button. So there are several repos for this project, all under the Tuco Flyer organization, right here. The bits and atoms that watch the cat. So a lot of the software has been in this bot controller repository. There's a bunch of other stuff, including the CAD designs. And I just started this new repo just as an issue tracking repo. So that seems to be the way to do things in GitHub if you mostly want to track issues independently of which of these separate repos they're in. There might be a case, for example, for bot controller to have its own issue tracker as well eventually, but right now it seems simplest just to centralize them. So we've got this, and I've been trying to just put everything in here that I've been like writing down as sticky notes and trying to fix. So what is this? Oh yeah, flyer shell, not winch shell. Yeah, and so the couple of these that I'm already working on, I've got parts on the way to do a lighter version of the leash. Today my plan was to look into issue 10, the flyer LED signal integrity problem. We were looking at that last night, and I think it's a bit more complicated than I initially expected, so this could be a bit of a mystery. You'll also right away notice the roll on the gimbal is completely wrong. I don't know why it's so much worse right now, but so this is now issue 4, the gimbal roll adjustment. I have a new theory now that it's so bad. So I tried a couple times, both right before starting this stream and on last night's stream, or yesterday evening, I guess it wasn't that late. I tried starting up the gimbal while holding it in a particular position on the theory that maybe it needed a stable position to initialize like a horizon reference or something. I doubt that would be super required, but it seemed like worth testing. As far as I can tell, even when I try to hold the gimbal perfectly level while I apply power to the gimbal and while I then turn on the motors, it still does this. I've got a new theory for why it might be doing this. I think perhaps there's a value that's supposed to be getting zeroed in SRAM that tells it like what the current target value for that roll axis is. And it's possible that in the normal code path, where you're running this off of like an RC servo controller, that gets initialized, but in the kind of serial remote control code path that we're on right now, that might not get initialized, which is a thing. There's definitely initialization code that gets skipped or just that works differently depending on which of those code paths you're on. And so it's possible they're expecting the Windows client or whatever normally connects to this thing to send to like zero some values before turning on the motors. There were a couple of those that I recorded in the original logs from that really, really tiny utility that was really all we had access to. And I haven't reverse engineered to see what those actually were, and we could even just like try poking those values and see if they help. So that's something I'd like to dig into, because as you'll notice, the camera is very lopsided right now. So anyway, my theory was that maybe it started doing this recently because there's that value, there's some value we're supposed to initialize and aren't, and that maybe maybe somehow we just ended up like initializing the micro with like a kind of unfavorable value in there. Like I think it's basically just maybe uninitialized SRAM. So we power on, and that if it's been off for a long time, maybe is in kind of an indeterminate state. But if we power it right back on after turning it off, then we're probably going to have a value that's similar to what we left it in. So that's one theory. Don't know if that actually is correct at all, but we'll have to do some experiments to figure that out. Some of the first couple experiments would be to maybe look at those values that I saw that maybe we're supposed to be zeroing and aren't, and just to like try to cross-reference those to other things. And then to also just try to get a better sense for how the roll controller in here is set up and how it usually gets its defaults and how to maybe adjust those. So that's a thing to work on in the near future, bug 4. So because of issue 4, this video is going to be really tilted right now, but I think I can at least fly this around and show you how it watches my cat a little bit. Where is Tuco? He was just over here. Oh, there he is. So from over here, I can tilt the gimbal over. Oh man, this is so tilted. I can't even get to Tuco from here. Okay, so I can move the flyer. There he is. Overshot a little bit. I still sometimes go up when I mean to go down. I'm going to the other side of the shop, maybe. So yeah, it's getting better. There's still obviously some motion control unsmoothness because the control for the winches right now is still like just barely written. Like it's definitely incorrect. It makes some just very, very incorrect assumptions about what the geometry is, and it's locally correct when the winch is like in the very middle of the room, but definitely needs work. So that's part of what's causing the wobble, is that we move the winches by the wrong amount and then have to kind of oscillate while we find, while we kind of get them back into their happy operating range with regard to the force sensors. So that's part of it. A couple folks are showing up in chat and saying hi. Got a hello from Adam in the YouTube chat, and Alex and Dean and Gitter. Nice to see everyone. Alright, so I had to drive this around a little bit, especially for folks who maybe are just tuning in on this stream and haven't actually seen this thing operating recently, because it is actually working pretty well. Oh, where are we? Oh, we're hitting the lower end stop on the gimbal. I need to move the robot, sorry. Down? No, that's up. Down. Where is he? Oh, there he is. Oh, that camera is so steeply rolling right now. Oh, Tuco brought me a bolt. It's not quite keeping up with that. And it hits the end stop right there. There is something really noisy happening outside today. I don't know what that is. Ah, we have another hello from Australia, it looks like, from Sean. Hello. All right, well maybe it's time to fly this back over here so we can inspect the electricals. As you can see, there's a little more like wires hanging out than usual. I added some connectors interposing on the LED bus in a couple places so we can take a look at it on the O-scope and continue our investigation. Now I just get to pilot this thing kind of like it's an RC aircraft. Let's get it into a good spot. I just abruptly stopped it, getting a little overeager to hold it at the position I'd found. But yeah, I think that worked. And I might turn off the gimbal while it's misbehaving this badly. All right, let's get the scope out. Yeah, I thought the biggest noise we'd have to worry about was my dishwasher. I didn't realize we'd have, like, whatever that is outside. It could be like anything with an engine, I guess. Like there's always construction around here. Just sounds like a fan over there. Well, here's another fan as the scope boots. Also seems like it could be like a dust collection system or something running in the unit downstairs from me. I don't know. The scope is still booting. Scope is booting, drink some coffee. Alright, actually I should be using this camera to illustrate the actual problem we're debugging here, or at least the immediate symptom that we've got currently. So, oh jeez. So these LEDs are misbehaving. It may or may not be visible, but the top row and some of the LEDs on top, you can see some slight shimmering where there really shouldn't be. Like it's oscillating between the correct value and an incorrect value. And there's one or two LEDs over here which seemed to just go full white for part of the cycle. So I originally assumed that this was just a pretty vanilla 3.3 volt signal integrity problem on LEDs that are happier with 5 volts. So I figured we'd just stick a level shifter in there and be done with it. But I wanted to actually try to pinpoint the problem so that we were sure we were solving the right problem before I do that. And I think that was a good idea because I saw something really strange on the scope. And for suspense value, I'm going to see if I can catch it in action before I describe it. Oh, Tuco brought a bolt back to me. Hey, Fuzzo. Alright. I'm going to ignore the clock signals, I think, and just focus on the data, although, actually, now that I made slightly better breakouts than I had last time, because previously we were just kind of haphazardly sticking scope probes through heat shrink, and I made these little breakouts, which might actually be nice. So maybe we could put the input and the output on here. So that's data. That was data. Huh. I hear you, Tuco. Is there just some... Oh, I think it just had a bad connection there. I mean, it obviously had a bad connection. I mean, a bad, like, mechanical connection, to clarify. It wasn't sitting on the right part of the wire. Oh, man. Can I has daisy-chained grounds? That's probably a bad idea. I think that's an alright connection. I mean on the ground, that one. Jeez. Okay. We still have the one and only bug. We didn't add another bug by attaching that scope probe, which is good. There's the packet. Alright, let's hook up at least one more scope probe. There's also a bit of a high-pitched noise, but I think that's coming from the equipment outside. Kind of hard to tell, honestly. Okay, now I get to be on the next side here and try to figure out which one is ground. I hear you, Tuco. Alright, I think if I clip on over here, that's ground, and will not be shorting out the 5-volt rail. Oh, let's go back to the right video channel. Yeah, check that. So let's dig a little deeper into here. So, I don't have the clock. Maybe I should just put that on there just for completeness, because I think that'll make a slightly better picture. I don't think that'll be super interesting, but let's just get clock and data for the input and the output on here just to show the whole picture. Since I think the clock delay might be a little bit relevant. I mean, not for this particular bug necessarily, but just for explaining what's going on, if we're going into detail on the waveform. Probes. Ooh, some offness. Oh, interesting. Okay. So the slight bit of glitchiness that you're seeing right now, I don't think that's actually the part of the problem. I think that's just because my triggering setup is not perfect. So I wouldn't worry too much about the flickering you're seeing where the whole waveform doesn't really line up right. I mean, there could be a problem in there that I wouldn't completely rule out, but I think it's just that the hold off on the triggering isn't always ignoring the rest of the packet once the packet starts. So, from the top down, the yellow trace is the data going in. That's coming from the SPI MOSI port, so the like master data out port on the microcontroller. And then green is clock, and you can see that it's just clocking out 1 byte at a time until it's done. That's just all it does. And the timing should be pretty predictable because it's all done by hardware with DMA and a FIFO in between the memory arbiter and the SPI engine. And then on the bottom, that's what we're seeing for clock and data after the signal goes through one of the groups of LEDs. So the signal is daisy-chained through all of these serial smart LEDs, the APA102s, and the serial data starts off on these 4 groups of 7 LEDs on the top of the flyer, which people were asking, like, whoever sees the top of the flyer. Well, there's sort of like a balcony area up there, so I actually see it kind of often when I'm like up there. But I think I might also have like an overhead camera, like for example. There's this overhead camera if we wait a sec for it to load. Oh, there's Tuco. And so like on here, we can actually see, I mean, you can see it right now actually. If I point, you can see these 4 bars that are just kind of fading. Each of those bars right there, if you were looking closer, you would see 7 individual LEDs. And they're undiffused. I figured they might make interesting kind of points of light for computer vision purposes later, but that's kind of like a thing that I added just in case. And then down here, this is really more of the like human interactive part of the robot. So like if I have LEDs that indicate the status of the camera, I wanted those LEDs to be near the camera. So that's what these rings are for. So they're daisy chained such that I think I'm just going from the 4 things on top down to top ring, middle ring, bottom ring. And if you go to the source code, you can actually see how those are laid out. So that's all done in bot controller. Source, LEDs. It's broken in bits and pieces. It looks a little bit like some of the stuff that I would do with Fade Candy, but it's not quite as complicated yet. So we had this idea of creating a model, which is a description of what each LED does. So it's just a data structure which is laid out the same way as the actual LED strip, but it has an LED shape template that describes like what the LEDs are used for, and then you kind of call these functions that take that template and like stamp out individual LEDs. I think those are pixel mappings are the individual sort of per LED objects that this creates. So you can see here, this is actually the function that defines LED mapping for the flyer. And this is called at initialization time to compute this kind of per LED data structure. So it starts out by adding those 4 strips on top. Then it can just in order add the upper, middle, and lower rings on the bottom. And so if we changed how the LED strips were daisy chained, we could just change this function correspondingly. This is also how things get a coordinate system. So that's what we're expecting to see. And so the blue trace is data after it's gone through those first groups of 4. So that's what, 28 LEDs. Or groups of 7, sorry, 4 groups of 7. And then the clock is delayed a little bit. You can see it's actually, from here, it looks like it's only delayed by a half a clock cycle. That's interesting. I would have actually expected it to be delayed by a bit more. That is interesting. I mean, I think this just doesn't have anything to do with clock synchronization. I think it's probably just a propagation delay at this point. So I suspect if we measured just like a single LED, we would just see that waveform shifted over, like not an integer number of clock cycles, but just based on the time it takes for the clock to propagate. So we're just seeing that add up a bunch. I saw some estimate of the extra number of clocks that you need to put at the end of the packet, but I don't think that's actually based on the clock delay, because the clock and data in this case are being delayed at the same time. But I think there's also something where each LED, I'm getting a little ahead of myself. There's a header and a footer on the end of each frame, and there's some weird feature with these APA102s where they consume part of the footer, so you need to increase the length of the footer depending on how long the strip is. But I don't think that's what we're seeing here. I think this is probably just propagation delay. So it looks pretty similar. Doesn't seem like the bits are being interpreted incorrectly. Although, so these are ones. The clock is going through, but the bus is still idle as far as this LED is concerned. So the signal is going out to the beginning of the LED strip, but we haven't actually started the frame on that LED strip as far as it's concerned until we get down here. This is some weird timing too. So we don't actually start sending data. This is like going from idle to the preamble state. So 1 here is idle, and 0 is going to be like I haven't started sending data until you send out a word that has a start bit in it, is the way the protocol is set up. So this is sending out just like empty frames for a while. I mean, frames, I'm overloading that term. It's sending out empty words, so empty 32-bit words that are set all to 0. And so while the top trace, as far as that LED is concerned, its frame of graphics has already started, or like it's starting. So this, right under the cursor right there, that's the first actual pixel. Those three bits are the start bits for the first pixel, and then there's a brightness and an RGB. But everything before that is preamble. So according to the LED further down the chain, the preamble is being extended. We also got more idle time, which is interesting. I don't know what the relationship is between the extra idle time and the extra preamble. It might just be like propagation delay within the chip. But now we've got a bunch of preamble where it's all 0. And you can see if we follow the actual pattern on the top, you can see these groups of LEDs that are all kind of doing the same thing. So let me position them at the cursor. So like right there, and to be clear, when I say cursor, I'm talking about that little hollow triangle that's kind of in the middle of the screen. It might be a little easier to see if I turn on one of these cursors. Can I turn on just one of these? I don't know. So right now, between those two vertical lines is 1 bar of 7 pixels. And then I can shift that down and get the other, the other bars of pixels. Whoops. So that's the second one. This will be the third one. And that should be the fourth one. And the right line here now should represent a boundary between the pixels that were consumed by the top LEDs here, and then the pixels we want to pass on to the rest of this. And so far, to be clear, I'm not actually showing any bugs. This is all just an illustration of how it's supposed to work. So here, after some delay, so I'm going to set these cursors now to show you where the pixel is kind of coming in and where it ends up. So this solid line here, the one labeled X1, that is the beginning of the first bit in the rest of the frame, the part we're passing on, as it comes into the strip. And then as it goes out of that sequence of LEDs, it's delayed a bit, and the first bit is right here. That is interesting. So we definitely have a delay in there that's like a number of clock cycle delay, because you can see that the data is shifting relative to that pattern of groups of 8. So at the very beginning of the strip, those groups of 8 were lined up with the bytes coming in. But what's happening is that there's a shift register apparently in each LED. There's at least like 1 bit being shifted off at some point. And so that shifts relative to the timing of that clock pattern. So that's interesting. So that dotted line there is actually the beginning of a byte, but it doesn't appear in the beginning of that kind of group of 8 pulses. So one of the bits looks a little longer than the other. But that is just 3 bits, and then the rest of the pixel. So that's all how it's supposed to work. That's part of the LED strip, kind of taking some pixel values, chomping them off, turning them into a longer header, plus a little bit of delay, and then just sending everything else on. So I think that part is all working fine. But, and then if you look at the, sorry, I shouldn't have said but there. We're trying to change topics too early, always getting ahead of myself. So if you look at the next section here, which is being passed on, you can actually see the outline of that wave pattern going through. And again, it's a little flickery, but I think that's mostly my triggering not being perfect. And there's a little discontinuity there where you see the blip disappear and then a different blip appears. Those are the discontinuities between rings. So you can see, like, if you assumed that first one wrapped around, it would be contiguous, but then there's a gap between the first ring and the second ring and the third ring. Now we're starting to see something wrong. So there was something flashing on our LED strip, right? And now there's something flashing on the oscilloscope. So I think those are related. I think we've found part of the problem, at least. And it looks like we have a pixel that has no start bit, or no start bits. There are 3 start bits in a valid pixel. So I think what's going on is we have an error in the frame that's being sent out, and like, it looks like maybe, let's take a closer look at what's going on here. So it looks like that's always an error. Like, we're always missing that start bit. Well, let's take a closer look and actually count the bits in a second. But just from this granularity, it looks like we're missing that sequence. And that causes a gap in the frame. So we end up kind of going back to that, like, preamble. Like, so the LEDs at the top are actually starting a new frame, and they're displaying another set of pixel values that are being captured from this part of the buffer. And as a result, we're getting another extra long preamble on the packet coming out of the LED strip. So I think what's going on is that that gap we're seeing in the yellow trace, which is caused by, we don't know yet, that's then causing the rest of the LED strip to process it as a new frame, which is giving us the much larger gap in the blue trace, which is then giving us the flashing LEDs on the subsequent LEDs, which are then getting, like, zeros, which are probably just going to end up resetting part of the internal state instead of having the PWM continue. I think that's what we're seeing. Yeah, these chips seem to process zeros a little bit inconsistently. Like, I've already noticed that some of the APA102s I have, if you give them a 0 value for the PWM, then sometimes they can treat that as being fully off, even if other PWM channels are on. So, like, if you have the current limit set to a non-zero value and, like, green and blue set to something like, you know, arbitrary, like 1 or 2 or 100 or whatever, and then you set red to 0, the whole pixel goes off. So I had to add a specific workaround for that in the code. It's kind of weird. Okay, let's just take a look at the input trace. Let's hide the output trace for the moment. We could also just decode this as SPI, and it might be a little easier to work with. Let's actually do that. None of that. Frame timeout. So one thing to watch out for is the way that the data display works on this oscope. It lines up the left edge of that text at the point where it first starts displaying it. And then after that point, it's not actually lined up. So if you see like the hex numbers, they're obviously taking up more space than the waveforms. And so they're just lined up at the left edge of that box, which can take a little getting used to. So we've got to go in some more. Actually, I guess it was useful to have those other traces for locating the problem. So you can start to see the pattern as I kind of unsquish these numbers gradually. Each pixel begins with an E. That's the 3 bits at the top. It might be F2 if it gets bright enough, but most of these are E's. So it goes E1 through E5 as it ramps up the brightness, and then there's red, green, and blue values after that. Same pattern until, and then there's 3 zeros. 3 zeros. And then an E0. Is it framed right after those 3 zeros? Let's check that. So here's a black pixel. Looks like we've got black pixels. This is looking like a firmware bug. We need to double check the Ethernet frames to make sure that this isn't actually in there. But I think that somehow the firmware is inserting some extra zeros into the outgoing packet or deleting a byte. One or the other. So it could certainly be like a firmware buffer overflow of some sort. And then here the frame starts again on the output side on the blue trace. Just looking at the end here to see if that's lined up. Got the E zeros, and then some EFs. Is it possible the SPI device like swapped endianness somehow in the middle of this packet? Because that's what it looks a little bit like. I don't know why we'd have an E0 at that point. Huh. And then we've got a bunch of FFs in the footer. Actually, am I just mistaken about the endianness? I should double check that. I thought that it was big endian and like E0 would come first, but like that's certainly how it looks from the beginning of the packet, and I thought that was what I remembered. Well, I think the next step is maybe to get like a TCP dump live of what's going on here. Oh, where can I get that? I think I have to go over back to this Windows machine. We were using Wireshark for this before, which was not amazing for the job, but it might be the best tool I have handy. That should be enough frames captured. Start filtering this. Oh, like that. Saved our previous filter. Oh. Why is that? There we go. These are all the same length. It does not look like that has the problem. Let's get a much closer view here. Three extra zeros. Oh! Is this after the end of the UDP packet? Could that be? Oh, this might be on the boundary between the UDP packet and the extra data in the frame buffer that we're not writing to. Oh. You know what I bet is going on? I bet the Ethernet frame is being rounded up to a multiple of 4 bytes, and then we're using that size to calculate the size of the UDP payload. And so we're getting a little bit of extra padding in there, and then writing the padding bytes to the frame buffer, which is of course not in the right format and causes the frame to end prematurely. That's got to be it. We could work around this by sending a larger buffer in software, but the real fix is in the firmware, so let's just fix it for real. It's not like we have to reflash all the microcontrollers to do this. And this is already on my desk here, so let's just do that. Let's head over to the Mac to do this so we can mount the Raspberry Pi file system easily. This has got to be the problem. You can add a little bit of debugging just to make sure, but I'm pretty confident this is the right direction. Not that confidence is really worth that much, but at least I feel like this would be a good waste of time. All right. My desk is so covered in scope probes. Bot. Yep. Well, the Raspberry Pi is still happy. Using SSHFS to mount the Raspberry Pi's home directory. This is not amazingly reliable, but it works plenty well enough just to edit source code files. And then I run git locally on the Raspberry. I'm just going to open that whole directory. Bot, firmware. LEDs. Alright, so we have an LED clock, we have a maximum number of pixels, we have a static frame buffer. So the beginning of the packet there is hard-coded, the end of the packet is hard-coded. So that end is actually way back here, and I think we've got a bunch of zeros here, which are just data that was in this pixels array that was not overwritten by the incoming packet. I think the straightforward and clean solution here is to make sure that we round the number of pixels down to a multiple of 1 pixel, rather than just letting it copy any number of bytes. So, like this exactly. This is a little bit more complicated than you'd think it might need to be because the network stack represents packets using a linked list of buffers, because it's common to have to take packets apart and put them together. So this operation avoids a lot of memory copying. And so what we're doing is we're actually intentionally copying memory by walking that list of packet buffers and copying chunks back to the frame buffer. I forget why we're doing this the hard way, or if there's a better utility for dealing with these pbuffs in this library. If I remember right, this is just kind of the normal way of accessing a pbuff. I don't think this was especially abstracted. And the thing is, we don't actually want to enforce that the individual buffers are on pixel boundaries, just that the entire copy is a pixel boundary, which that's a problem. Like if you have one packet which has part of a pixel, another packet that has the rest of the pixel, you have to look at both of those packets and then decide that you don't have enough data to write the entire thing. The other option is I just have this loop add the rest of the padding explicitly. Maybe I should do that. This is where the default padding is set up. Maybe, I do think I want it to be the behavior where we zero the portion of the frame buffer that isn't being set here. And I don't really care about spending the CPU cycles to zero it, so I think I'm just going to unconditionally zero it just to reduce the possibility of bugs like this in the future or present. All right, that is the value we should be sending when the pixel's off. I'm going to initialize it to that value. I'm actually not sure under what circumstances these would be fragmented. So actually, I should probably redefine this comment to say that we're doing this for sort of full compatibility with the data structure, but we should be getting a single pbuff for all the packets, just because these are being received pretty much directly from the network interface. Oh, there are just so many reasons to zero this. That actually doesn't, that doesn't help if the padding is in this length though, right? Like we're writing zeros. The problem is not just that we're leaving that. So like really we would need to back up to the last proper pixel boundary. Oh, sorry, that was under the scope while I was doing all that typing. So yeah, overwrite the remainder of the frame buffer starting after the last complete pixel written in order to clear any previous larger frames, as well as to avoid sending padding bytes or incomplete pixels to the hardware. So... Oh, Len's asking where Tuco is, my fuzzy little Valentine. Where is Tuco? Yeah, he is my favorite little boy. Where is he? I don't see him around here. I'm assuming he's probably hanging out upstairs, but I'll maybe call him and see if he wants to hang out. It's strange, but like that's the noise he seems to respond best to. My bad C urges are coming, and I really just want to like clear the lower few bits of this pointer, which is probably fine. I might just like rewrite this to be a little bit less like low-level curmudgeon C and more like slightly modern C, since you don't need to hold the compiler's hand this much like you may be used to. That said, I am actually just formatting this as beginning and limit. Oh yeah, because pixels and yeah. At least those are uint32s. Oh, hey, buddy. He did come. Oh, you're such a good boy, Took. Oh, Oh, yeah. Wow. Yeah, a little hard to watch too while I have the O-scope hooked up to the flyer. Well, I think we figured out what the problem is, so I can maybe unhook it. Now the camera roll issue. Yeah, I don't know that actually changing it elsewhere is going to be better. Like, I mean, I could write an offset of macro and like change a lot of how this works, but I think I'm just going to do this the way which is maybe not straightforward to people who don't spend a lot of time in C, but is very straightforward to me. Which would be, we have to do a little casting, but so we're taking the lower 2 bits here, which is 3, if you look at the binary. The lower 2 bits are set. We could also write that as something like, we want 2-bit set, like that, but that's kind of ugly unless we actually write a macro to do it, so that's usually a little more straightforward. So we're masking off the lower 2 bits. This ands the, I mean, I don't know if I need to explain bit arithmetic. It's probably useful for some people. And some people are like, don't go into that, that's stupid. And some of you are like, what are all the squigglies for? I'm basically just taking the low 2 bits and setting them to 0 by bitwise anding those bits with 0 and the rest of them with 1. And doing that as an integer, which is the same width as the pointer, so that I align it with the next previous, or with the previous 32-bit boundary. And then I just want to loop until that is, oh, you know, actually, I do want that to be 32-bit because I want to write these 32 bits at a time. Let's limit. Yeah, I'm gonna try to rewrite this without all the pointer garbage because I think we can do without all that. It's like, obviously we could make that work, but I just don't like the aesthetic of it. And so I think I'd rather just stick to indexing into pixels and editing bytes out of it. I'm happy to cast that into bytes and edit the bytes, but beyond that, I think I'd rather avoid it. So let's do it this way. Let's alias pixels just for fun. We will also be able to access it as bytes. Byte offset. This is when I need to know how many bytes are in the buffer. I think I'll just use size of, and then use LED max pixels for the word count, and that's pretty straightforward. So byte offset points to the next byte that we're going to write. That has to be less than. If it's equal, we've just stepped past the end of the buffer. And then that's the data in the pbuff. Yeah, and we're just copying this byte by byte with limits. We could use memcopy, but then the setup would probably be more trouble than it's worth. Okay, so we're walking through the data buffer. We're just using a pointer to walk through the payload buffer, but we're using this byte offset for the output index. Same otherwise. And then at this point, so that truncates off any incomplete pixels. And then we can just use that constant again, which is LED max pixels. That's closer to what I wanted. Let's try that. Oh, Took's on the rack again. I gotta get this working. Pixels. Len is suggesting something that wouldn't be correct. So at least modern C compilers with the flags that I would prefer to compile with won't let you do that without a bunch of casting, first of all. Or at least they'll complain a bunch. I think they'll let you compile. I think it'll compile, but it'll give you a bunch of warnings. And that also masks off 4 bits, which is way too much. I want to mask off 2 bits. Multiples of 4, but not 4 bits. Did I compile this? No. Incomplete pointer type. Oh, incompatible pointer type. Can I not cast directly there? Oh, duh. My cast was to the wrong type because, like, I just wasn't thinking about it. Or no, sorry, I meant to change this. My variable was of the right or wrong type, and the cast was of the right type. So you have 32-bit pixels, 8-bit pixels, and a 32-bit offset. All right, let's program this. See if that fixes the bug. I'm attaching this to USB carefully. There it is. Alright, so it's flashing and the scope is not updating. I still see the LEDs flashing. Yeah, that didn't seem to have fixed it. Did I just mess that up? Well, I'm tempted to just like start debugging this by like going through my checklist of, well, first of all, let's just make any change to make sure that we're like in the right thing and compiling it all correctly. And then let's maybe change this to a different value to see if the fill is working properly. You know what? Those are E1. Wasn't our fill E0? Where are those E1s coming from? What was the end of the packet like in Wireshark is my next question. IP. So yeah, we have those E1s at the end of the packet. Why did I make those E1s specifically? Oh, right, because I think the brightness code right now clamps the current limit to a minimum of 1 because I was seeing this nonlinear or like a discontinuity around 0 otherwise. So yeah, E1 is the lowest current limit value that the Rust code will use right now, but E0 is still a valid pixel value, and the firmware should be able to set that to E0 without consequence. So it's interesting that what looks like is going on is, like, it's almost like we're getting 3 garbage 0 bytes, and then just like copies of maybe some other part of the frame buffer which does have an E1 in it. I don't know where that would be coming from. But yeah, these UDP packets look entirely unsurprising, which is good. Let's maybe perform some experiments without the Rust code, just like netcatting some stuff into this. So, yeah, let's go back to the Windows machine. Alright, so I'm going to Control-C the bot server. What was the opcode for these packets? I think it was 2, but I'm going to look it up just because I don't want to send the wrong packet to the flyer. The last thing the gimbal needs right now is more garbage in its serial port that it might react badly to. Alright, that was in botcom. 5, right. 2 was sensors, which wouldn't have done any good. Alright, can I do this? I'm gonna have to look up some kind of cheat sheet for opening UDP socket in Python. Yeah, that's what I was looking for. I always have to look up the options for stuff like this. I've never been any good at remembering completely arbitrary stuff. fig file somewhere. Ah, 9024. Oh. So there's one word of preamble, and then my 1, 2, 3, 4, 5, 6, 7, 8, and then 3 0 bytes all over again, like I didn't do a darn thing. Yeah, I wonder if this is happening like at the struct padding level? I don't know, but it's something at a different level than I thought the bug was occurring at. It rounds it and then adds the 3 zeros. So that was an improvement, but didn't actually solve the problem. Three zeros and then a bunch of EOs. And are the EOs even the right footer? I thought the footer was a different byte, and this was just some other garbage. I mean, EO is my empty value. What's an end? End's FFs. Yeah, this is super weird. It might be nice to dive into some like on-chip debugging at this point and like step through this code a little bit. How much of a pain is that to set up? I don't know if I've actually done that here. This is not exactly the chip we're using, but same series. Oh, no it isn't. This is the STM32. Oh, this one. Yeah. Okay, OpenOCD, TII, CDI. I wonder if we have a new enough OpenOCD that this is just built in. We could also certainly use a different debugger other than the one that's built in. I've used the Blackmagic probe with this before, and that was a nice experience. MakeOMK says, surely it should be filling the rest of the LED values with your empty value. Well, that's what I would expect, sure. I mean, the question is, where are those 3 0 bytes coming from, right? Let's see if we notice anything different at the end of the packet, actually. I've only been looking at the beginning of the packet. It'd be nice to have a little test sequence that we can run through here. really going to do this on the REPL? I think I do just want a single packet sent at the moment, and that'll be fine. I was thinking about looping through packets of different lengths, but I think that might just be a mess on the scope. And it looks like the part of this that's processing the packet is doing the right thing. Maybe just oscillate between sending those two. Okay. So that 1 byte change is now kind of causing the whole thing to shift back and forth by 1 32-bit word. And with or without that, the 3-byte offset is there. Oh, is this just an endianness problem with my off value? Is that all this is? That's got to be all this is. Never mind. I'm making this into something quite more complicated than it actually is. Okay, never mind. Let's fix that. Oh, did we just lose that camera? Okay, rebooted the webcam. Is this camera still good? Kind of. Yeah, so maybe MakeOMK was right. It was filling it with my empty value. I just didn't recognize my empty value because the endianness was wrong. That would be a nice, simple bug. Sort of thing I could spend hours debugging. Yeah. Do I have any kind of static endian swap macro here? Oh man, this keyboard not being on a level surface is really messing with my finger happiness or whatever. Typing funness. Just can't have any fun with the typing. Oh, are these macros? These are often defined such that you can't rely on them to be macros or functions, but yeah, we do have that. H to NL is exactly what I want here. So this is like POSIX standard byte swapping, but they have them in the in the network driver, of course. So we can just do that. Is that all we needed? Was that the entirety of it? Yeah, no, I mean, in hindsight, the Indianness thing is just obvious. I just didn't see it at the moment because I was too busy trying to do too many things at once. I have that experience a lot of the time when I'm like checking the archive on the stream, or like somebody mentions a problem. It's just like way easier to see something in hindsight when I'm not trying to multitask. I made some inconsequential change to this that's going to cause it to update the build. I do actually have some Python code to do this. I just like reinventing the wheel. Yeah, that looks right. Yeah, that was just an Indianness problem. And a padding problem, but that didn't even matter. The problem we were hitting was just the Indianness problem. The padding is just something that was good to do for completeness. Yeah, so sending bytes with the wrong Indianness in the part of the frame that we weren't even using, to recap, was causing the LED to think that another frame was starting and to then give us some corruption that manifested either as flickering or as the LEDs actually flashing on and off. But I think we're past that now, and I can just go back to actually implementing the LED animations that I wanted. Or maybe fixing the gimbal. Seems fine. Alright, well, let's check this in and go back to working on the Rust code. Alright. Well, let's put this bot slightly more back together so I can fly it around instead of just having it attached to the O-scope. The mystery turned out to be Indianness and blindness thereof. Andrew's asking what the current project is. We're debugging the LEDs in the flyer. I was just using the Raspberry Pi to flash code. Well, no level shifter or anything necessary, just some more attention to detail in the code. And that explains why we were seeing what looked like a 1 byte and then later a 3 byte gap. Once we looked closer at it. Alright, I'm going to put tape back on this just to bundle up the wires and keep them from getting quite so much in the way. This might be an even hackier job of taping it back together than before, because now all of you are watching, so I get to be extra messy. Okay. Guess I can turn the power on again. I'm curious if the gimbal is going to initialize with a slightly different roll setting. Maybe. It doesn't look good. Oh, Tuco's not on the rack anymore. Let's see if we can find him. Well, it is an improvement not to have the lights flashing completely incorrectly. Oh, I don't see a Tuco. Oh, that's almost a really good shot. Just a second here. That's kind of nice. Camera roll is obviously wrong now. Wow, the roll changes a lot depending on the yaw. See that? Which means that maybe the calibration we're dealing with is in a different coordinate system than the actual axes of the gimbal. See, that roll is not me. It's just doing that on its own after settling into that yaw. Squeak, squeak, squeak. Oh, well, let's do something useful. So right now the animation code on that bot is pretty much entirely placeholder. There's a lot of stuff that we wanted to actually do with that. The first thing it might be nice to do is actually have a way of defining animations relative to where the camera currently is. The code that's there right now is very placeholdery. Let's take a look at that. I'm also tempted to wrap up this stream and then start a new one shortly, going into the gimbal stuff in more detail. Because I think that's becoming a more pressing problem at this point. Like, the LED stuff would be really nice, like especially the streaming and recording indicator stuff, but now that the flashing is gone, it no longer looks just completely unpresentable, in my opinion. Yeah, this is the, this is the actual LED animation code for the winches. So it's based on a base color and then a couple of effects that layer on top of that, a motion effect and a flashing effect. So I suspect we'd want something similar with the flyer, having a way to kind of compose different sorts of animations together that would each respond to the flyer's state. I still got like commented out code. This was just turning on all the LEDs dim gray, which didn't really seem to show the bug. So for a while, like, I had that set up and it wasn't showing me what was wrong. And then I started writing code, and then I hit this bug pretty early on, and I didn't really want to hide the bug, so I left this alone for a while. Alright, well, I need to take a quick restroom break, and I think I'll also try to track down Tuco, but I'll be right back. No, Tuco? Here, Tuco. There you are. Hey, Tuco. Yeah. Oh, it broke off. Yeah, Tuco's been playing with this somewhat destroyed mouse. I mean, it's not a real mouse, but a leather toy thing. Okay. Oh, what do I want to do here, and how much of this do I want to do on stream? I don't really have that much of a plan for the top of the flyer at this point. I might do something more dynamic with it in the future, but right now I would actually be pretty alright just loading a static color for each of the LED strips from the config file. The rings, though, I kind of want to think about them in terms of building maybe some kind of animation utility for each of the rings that lets me define like a radial, like an angle that the animation is centered on, and then, you know, animations that kind of like flow in or out of the center point maybe, or rotate around it. Because I can imagine something that's sort of like a blip that kind of like radiates out from the current location. That might be a good little signifier for like you are here. One of the winches is really oscillating right now. But yeah, I'm starting to think maybe the gimbal thing is just bugging me, so I might get a bite to eat and then come back with another stream where we focus on the gimbal, because I think that's a little bit more urgent to my mind than LEDs. But at least now I can start to poke around with the LED animations and start to make something a little nicer. Tuco's running around on that sideways floor. Whoa. Now I'm having trouble going down because of the leash force problem. Is it really into Tuco's tail right now? It lost the stick again. As soon as it loses the string, Tuco's like, where's all the pulling? It's dead now. Yeah. Alright, well, I know that this has not been the longest stream so far, at under 2 hours even, but it looks like that problem turned out to be embarrassingly simple. And so I think at this point, I'm going to get a bite to eat and then start up another stream where we can try to dig deeper into this gimbal issue, because that's a little bit more bothersome to me than the lack of fancy animations at the moment. So I think that's the plan. And as always, thanks for joining us. If you enjoy this sort of thing, I try to stream pretty regularly. You can follow me at scanlime live on Twitter, or follow scanlime on Twitch, or follow me on YouTube, and you can find out when I'm going live. And there's edited videos at scanlime.org. I should put together another one soon on this winch. I'm just trying to get it to the point where it's a little bit more presentable for that. But yeah, I got to get back into video editing for that ASAP. And then, yeah, just thanks so much for stopping by, and thanks to everyone who supports the channel with hardware, with sending a few dollars my way to help me pay rent and buy cat food and, you know, buy hardware. But also thanks for people who send in hardware and books and cat toys. That stuff is super appreciated, and yeah, it helps us keep going. So I will see perhaps some of you soon after I get a bite to eat and do a little bit of pre-planning for this next stream, and then we can dig into some gimbal code. So thanks a lot. I'll see you all next time.